Everything fine? Do you see my file?
Yes.
Okay. For me, it's a pleasure to introduce Professor Vicentiu Radulescu. Professor Vicentiu Radulescu is professor in Department of Mathematics, University of Craiova, Romania, and the University of Science and Technology in Krakow, Poland, and the professor of Institute of Mathematics of the Romanian Academia, Bucharest. Professor Radulescu has published more than 400 articles, and he has won more than 20 awards and distinctions. And his editorial positions are editor-in-chief and founder of Advance on Nonlinear Analysis, editor-in-chief Bulletin of Mathematical Science, editor-in-chief in Boundary Value Problems, and the editor Journal of Geometric Analysis, editor of Mathematical Methods in the Applied Sciences, editor of Asymptotic Analysis, Complex Variable Analytical Equation, Rede Conte del Círculo Matemático de Palermo, Opúscula Matemática, and Journal of Numerical Analysis and Approximation Theory. Please, Professor Radulescu, you may now begin.
Thank you very much for your kind invitation and for your introduction. It is my pleasure to give a talk in your seminar, and I have chosen a research topic, the interplay between local equations and the non-local problems. In this framework, I shall discuss some examples of solutions, for instance, normalized solutions or solutions with prescribed mass, also ground state solutions for problems of this type, as well as several possible research directions in the future. In the first part of my talk, I shall discuss some results about ground state solutions of the so-called periodic Shokar-Pekar equation. Then I shall consider solutions with prescribed mass for the two-dimensional Schrödinger-Poisson system. I will continue with ground state solutions for the n Laplace quasi-linear elliptic equation, and I shall conclude with further directions, some perspectives related with the content of my talk. This is the abstract of my talk. As I have already mentioned, I shall discuss about normalized solutions and ground state solutions, and the main results in my talk are included in these three papers. The first one, in collaboration with Dongqin and Professor Tang from Central South University, published in the Journal of Differential Equations in 2021. Then I shall discuss about normalized solutions, a multiplicity property for normalized solutions for the planar Schrödinger-Poisson system with critical exponential growth. And I shall conclude with a very recent paper, which will be published in Science China Mathematics, always with Sutong Chen and Dongdong Qin and Shenhua Tang. In the first part of my talk, I shall start from this very famous equation, which is a Shokar-Pekar equation, and which contains a linear term in the left-hand side and a convolution term, so a non-local term, in the right-hand side, in the reaction term. The simplest form of the Shokar-Pekar equation is the following one: minus Laplace of u plus u in the source term equals to 1 over modulus of x convolution u squared times u in R3. Problems of this type were considered for the first time in the 50s by Pekar in relationship with the modeling phenomenon of quantum polaron. This model corresponds to the study of free electrons in a ionic lattice in interaction with phonons associated to deformations. In the approximation to Hartree Fock theory of one component plasma, Shockhard used equations of this type in order to analyze, to describe the properties of an electron trapped in its own hole. So equations of this type are in very close relationship with phenomena, concrete phenomena that appear in mathematical physics. On the other side, this Shockhard-Peccar equation is known in other books, in other treatises, as a Schrödinger-Newton equation in models that couple the Schrödinger equation that appears in quantum physics together with the non-relativistic Newtonian gravity. Such a model was proposed for boson stars and for the collapse of galaxy fluctuations of scalar field dark matter. In my talk, I shall consider in the left-hand side a related operator subject to a potential V of x, which has a very important role here, and in the right-hand side, again, the convolution between a potential and a function capital F of u times F of u, this time in Rn, and we are looking for solutions in the Sobolev space H1 of Rn. We observe the contributions of two types of potentials. So we are interested in the combined effects of these two potentials. From one side, in the source term, we assume that V is a continuous potential, which is one periodic with respect to xi for any I between 1 and n, and we assume this property of the spectrum of the associated Schrödinger operator that appears in the left-hand side of our equation, which is prescribed, which is described in this hypothesis V1. On the other side, concerning the potential W that appears in the reaction term, we assume that this one is an even function, and the property, the regularity property of this one is W is in L R1 plus L R2. Also, we assume that W is non-negative, and in a neighborhood of the origin, this is strictly positive. And we also assume this property, which is a kind of Cauchy-Schwarz property associated to the potential W, namely integral over the whole space of W convolution phi times psi is controlled by a constant square root of integral over the whole space W convolution phi times phi, and the same but with respect to psi. And this happens for any non-negative test functions psi and phi in L1 log of Rn. On the other side, concerning the nonlinearity that appears in the right-hand side, we assume that f is a continuous function such that the behavior of f is controlled by a constant times t to a certain power p1 minus 1 plus t times to the power p2 minus 1. So again, here we observe that we have an unbalanced behavior of the nonlinearity. So we have a kind of double phase problem. In this situation, we have this relationship between the two different exponents p1 and p2, which is described here. On the other side, the nonlinearity capital F is greater or equal to 0, and the behavior at plus infinity is described here, which means that capital F has a superlinear behavior at plus infinity. On the other side, another functional which takes into account the contributions of small f and capital F, which is denoted by hat f of t, and which is denoted here, the behavior of this functional is described in this hypothesis F3. Then we assume that the limit near the origin of f of t over t exists, and sometimes f is an odd function which is described in hypothesis F5. So these hypotheses are maybe a little bit complicated, so that is why I shall give here an example. For instance, if capital F of t has logarithmic growth, as it is described here. For instance, capital F equals to modulus of t times logarithm of 1 plus t squared, then f of t is defined in this way. Capital F hat of t is 2 times t cube over 1 plus t squared. And we observe that small f satisfies assumptions f1 up to f4 with these values of the constant. What it is important here is that this nonlinearity does not satisfy the standard Ambrosetti-Rabinowitz growth condition, which appears in the statement of the mountain pass theorem. Some remarks before giving the main result. For the positive definite case, namely where V, which appears in the left-hand side, is strictly positive, then the existence of non-trivial solutions can be obtained via the mountain pass theorem and the weak sequential continuity of the fresh derivative, as proved by Ackermann, who studied problems of this type under these assumptions and also subject to the Ambrosetti-Rabinowitz condition. But at the beginning, I would like to point out that exactly the same situation, which appears here, was studied in a seminal paper by Paul Rabinowitz, where he established the existence of ground state solutions, but without a non-local term in the right-hand side of the equation. Next, if the potential V, which appears in the left part of the equation, changes sign, but such that our hypothesis V1 holds, then problem 2 is much more difficult due to the fact that the associated Schrödinger operator, which appears in the left hand side, has purely continuous spectrum, which consists of closed disjoint interval. In this situation, Buffoni, Jean-Jean, and Stewart have considered this situation and proved the existence of nonlinear, non-trivial solutions in the simplest case where f is linear and the potential W, which appears in the right-hand side, equals to 1 over modulus of x. So, our question in this first part of my talk is to study the problem by getting rid of the Cauchy-Schwarz inequality, which is described in our hypothesis W3, which was considered also by Ackermann. In this situation, it is natural to ask us how to obtain the existence of ground state solutions for our problem, but without using the classical Ambrosetti-Rabinowitz technical condition. And the main result in this situation is the following one. We assume that the potentials B and W satisfy our assumptions, W1, W1, W2, F1, F2, and F3. Then our problem has a solution denoted here by U bar, which is non-trivial, which belongs to H1 of Rn, and such that, this is important, this is a minimum of the associated functional phi, which is defined here, which is strictly positive, but the infimum is not taken with respect to the whole space H1, but with respect to the set of stationary points of phi, of the energy functional phi. We observe that in the definition of the associated energy functional, we have two parts. The first part, the first integral, is associated to the left-hand side, while the second part is associated to the non-local term, which appears in the right-hand side. Even more, if f satisfies conditions f4 and f5, then our problem f5 is associated with the oddness of the functional f. Then our problem has infinitely many pairs of geometrically distinct solutions, of course, plus u and minus u. The sketch of the proof is the following one. First of all, it is natural to show that our set K of critical points is non-empty. Then we define the infimum of the associated energy function with respect to the set K by C0, and we prove that this one is strictly positive. Then we take a minimizing sequence in this set of the associated energy functional, so converging to C0 to the infimum. Then we prove that UN is bounded. So this means that that there is some U bar non-negative such that U bar is a critical point of phi, and such that U bar is a solution of our problem in the set that the critical value C0, which is positive, is achieved. In the next step, for any positive integer j, we consider the family sigma j of all closed and symmetric subsets A, such that gamma of A is greater or equal to 0. The index gamma of A greater or equal to 0. So this is associated to the Lusterner-Schnirelmann theorem. So we consider non-decreasing sequence of Lusterner-Schnirelmann values of the energy functional phi, which are defined in this way. Ck is the infimum for C greater or equal to C0, where C0 is defined here, such that gamma of phi C is greater or equal to K, where we prove that KCC is non-empty and CK is strictly less than CK plus 1. So this sequence is strictly increasing. So finally, we deduce that there is an infinite sequence UK of pairs of geometrically distinct critical points of phi, such that phi of UK equals to CK. So this implies the existence of ground state solutions of our problem. In the second part of my talk, I shall consider the very famous Schrödinger-Poisson system, which appears here, but with the logarithmic nonlinearity, no local term. So we observe that this part is a little bit similar with what we had before. Then in the source term, we have a non-local term, which includes the contribution of a parameter, then the convolution between the logarithm and u squared times u, and in the right-hand side, we have this type of nonlinearity, exponential of u squared minus u squared times u. The problem is studied with respect to the two-dimensional space, and what it is important here is that we impose a mass constraint, in the sense that the Lebesgue, the L2 norm of U in R2 is prescribed by a given number C, a positive given number C. Very good. Now, we also point out the fact that in the left-hand side, we have the contributions of two parameters, one of them lambda being a real number, and the other one mu associated to the non-local term being strictly positive. What it is important here is associated with the so-called critical exponential growth, which appears in the right-hand side. I shall recall here that a function f, this is associated to the fact that the study is developed in R2, in two dimensions. A continuous function f between R and R is said to have a critical exponential growth if there is a positive constant denoted alpha 0, such that if we take the limit at plus infinity, plus or minus infinity of modulus of f of t divided by exponential of alpha t squared, this one equals to 0 for alpha greater, strictly bigger than alpha 0, and plus infinity for all alpha less than alpha 0. This is associated with the pioneering papers by Trudinger and Moser, and it was considered in many situations in recent years. For instance, I can give examples here. The contributions of Adimurti and Yadava, who treated, I think, for the first time problems of this type. So this is a maximal growth, allowing to treat problems in a variational way. And also I would like to point out the contributions of Figueiredo, Miyagaki, and Roof in a very important paper published in calculus of variations and partial differential equations in 1995. So here there are only two seminal papers in this direction with the critical exponential growth in 2 dimensions. What about the motivation of problems of this type? To study problems that allow normalized solutions. In fact, this is due to physics, to mathematical physics, because physicists are interested in normalized solutions or solutions with prescribed mass because the L2 norm of solutions of this type is a preserved quantity with respect to the evolution process, and also their variational characterization can help to analyze the orbital stability or instability properties. A remark in this equation, studied in this equation, is that the reaction term which appears in the right-hand side is in some time inspired by Cassani, Tavares, and Zhang from a paper published in the Journal of Differential Equations in 2020, in relationship with the analysis of positive solutions of the Bose-Einstein system in R2. Bose-Einstein is very much connected with Ginzburg-Landau energy that describes singularities in the study of superconductivity or superfluids. The future of this contribution is the following one: the presence of a logarithmic convolution in the left-hand side, in the source term, in a relationship with the and which is also unbounded and which changes sign. The abstract setting for this problem: our problem has a variational structure, so the solutions are critical points of the associated energy functional phi, which is defined here. We observe here the contribution of the left-hand side. Also this one, mu over 4 W integral of logarithm modulus of x minus y u squared of x u squared of y dx dy, and this one, the last one, is the contribution of the reaction term. So, due to the fact that we are interested in the existence of normalized solutions, it is natural to study this energy function with respect to the manifold, with respect to the sphere. So u is in x, such that the L2 norm squared of this one equals to c. And x, the working space, is a set of functions in H1 of R2, such that the integral of logarithm of modulus of 1 plus x u squared dx is finite. This is again associated to the fact that we have a logarithmic term in the left-hand side. Then we consider the manifold, this one, which is the symmetric manifold, the intersection between x and the set of functions u in R2, such that u of x1 and x2 equals to u of modulus of x1 and modulus of x2. We have this symmetry property. We remark that instead of working on the space X, we can take advantage of the axially symmetry variational framework of our working space EAS, which is endowed with the norm which appears here, which is defined here, and u star, the norm u star of u, is defined in this situation, again associated with the logarithmic term that appears here. So that is why we shall work with the constraint hat SC, which is defined simply by the set of functions u in EAS, such that the square root of the L2 norm of u equals to c. This means that if u is a critical point of the energy function restricted to this manifold, then u is a critical point of u of phi with respect to the sphere of radius c. Besides helping to overcome the lack of compactness caused by the critical exponential growth, this type of axially symmetric setting has a lot of benefits to the proof of the L2 convergence of minimizing sequences and Palesmail sequences which is in many situations a real obstacle dealing with L2 constraint problem due to the fact simply of the lack of compactness for the embedding H1 of radial functions to L2 of R2. So the main theorem in this part of my talk is the following one. For any parameter mu strictly bigger than 0, mu is a parameter that appears in the left-hand side, there is a positive number, say C1, depending on mu, such that for any C small enough, C is associated with the norm of the renormalized solutions. Our problem has a solution denoted by UC and lambda C. Again, lambda C is a parameter that appears in the left-hand side, such that UC is in the manifold SC, so this is a normalized solution, which is greater or equal to 0, and such that this one minimizes the energy functional with respect to the functions U in the manifold SC, and such that the L2 norm of the gradient, the squared of this one, is strictly less than pi over 3. The second property in this situation is that for any mu strictly positive, there is another constant denoted by C0 strictly positive, such that for any C small enough, again less than C0, our problem has a second solution such that the level of the energy in this situation is strictly less than mc plus 2 pi. Let me please give some ideas of the proof. In situations of this type, when we handle problems with normalized solutions, it is natural to define the so-called associated Pohozaev functional. In our situation, this is defined by integral over R of the whole space gradient of u squared minus mu c squared over 4 minus this part, which is associated to the right-hand side. And we prove, this is standard, that any solution of our problem satisfies L2 Pohozaev identity P of u equals to 0. Then we look for a geometry of local minimizers of our functional phi with respect to this manifold under explicit conditions on C. That is why we define the set denoted here by A pi over 3, which is a set of functions u in the symmetric manifold E, such that the square of the norm of the gradient is less or equal to pi over 3, and such that for any u in this set, the Pohozaev manifold is strictly positive. There is some tu in between 0 and 1, such that the Pohozaev functional vanishes at the point t times u tu. Very good. Then we find an explicit value denoted by C1 depending on mu, strictly positive, such that for any C less than C1, phi has a geometry of local minima, in the sense that the infimum of the energy functional with respect to the C hat intersection A phi over 3 is strictly less than the infimum of the same functional, but here we take the intersection with respect to the boundary of this manifold, of this sphere, in fact. Then the next step is to establish that the local minima MC is achieved. This means that if UN is an approximated sequence with respect to the energy functional phi, then UN converges strongly to U in the space EAS. The crucial ingredient here in the proof of this statement is to establish the boundedness of the sequence or the norm of UN in X, and even more to prove this energy estimate which appears here for some C strictly positive, and this follows due to the fact that UN is a sequence in the manifold SC hat intersection A phi over 3. So these are the main steps of the proof of this result. And I shall conclude with another related problem, this type is again a local equation associated with the n Laplace operator. We observe that in the left-hand side we have almost the same situation. This is a kind of Schrödinger type operator, but quasi-linear in this situation, in the sense that here we have minus Laplace n plus again the contribution of a potential v of x times power type nonlinearity modulus of u to the power n minus 2u equals to f of u in Rn. This time n is greater or equal to 2, where v is a potential, standard potential, which is assumed to be continuous on the whole space, such that the infimum of v is strictly positive, and the supremum is finite. So v is a strictly positive potential, which is also bounded. Of course, there are plenty of open problems here. What happens if v satisfies other properties, for instance, properties, local properties or periodicity properties, and so on and so on. About f, the nonlinearity f, we assume that f is continuous, and it satisfies, you see, again, a kind of Schrödinger-Moser property. In the sense that there is some alpha 0 positive such that the limit at plus infinity of modulus of f of t over exponential alpha t to the power n over n minus 1 equals to 0 for any alpha strictly bigger than alpha 0, and this limit equals to plus infinity for alpha less, for any alpha less than alpha 0. And again, the behavior of f, the growth of f near the origin, is prescribed in this way. Also, we have a property of this type, which gives, in fact, the behavior of f of t times t minus n f of t. We have another behavior concerning the relationship between the growth of f and capital F. This is with respect to f. And with respect to v, again, we have this property, and v is one periodic in x1, x2, xn, and v star, the supremum of v of x over Rn, which is finite, as we see here, is strictly less than this very important constant, denoted by c star Tm, and which is denoted in, which is defined in this way, namely the supremum of n over ln norm of u to the power n times integral over the whole space capital of u, under the constraint that this norm of the gradient is strictly less than alpha n over alpha 0 to the power n minus 1, where alpha n is defined in this way. Next, again, the problem is variational, so we define the associated energy functional, which appears here. Again, this is a contribution of the source term, this is a contribution of the right-hand side. And it is important again to point out that we define here the set of critical points of phi in the standard way, but also it is very important to use the Nehari manifold, which is a set of points in W1n, of course, minus 0, such that phi prime of u applied to u equals to 0. This is important because in many situations, instead of taking the infimum of the energy functional with respect to the whole space, we take the infimum with respect to the Nehari manifold, and we can obtain very, very striking results. For instance, in the study of double phase equations, this is a standard way to proceed. The theorem in this situation is the following one. Under these assumptions, our problem has a ground state solution denoted by u tilde u, which is different to 0, and this means ground state solutions, that this solution is an infimum of the energy functional, this time with respect to the set of all critical points. The sketch of the proof is the following one. Using our first assumptions and the suitable energy estimate, we use a mountain pass theorem in order to get ceramic sequence denoted by UN corresponding to the minimax level C star. Then we prove that this sequence is bounded. Then we establish two compactness lemma for general nonlinear function W1n. To verify that the sequence UN is non-vanishing, we generalize the result established for radially symmetric spaces. I have given here some ideas, some previous papers. Since our equation is quasi-linear, the functional Bu and V, the bilinear functional Bu and V denoted here is not linear, is not bilinear, and it requires to verify that Bu of Bun and V converges to Bu bar V for any V in W1n. This is done again by analytic techniques applying the results of Cherrier. Then, using the unified conditions Vf, which appears at the end of our statements, a special part will be constructed to control the minimax level C star such that C star is less than this value, and this allows to restore the compactness for the critical case. Very good. And for the periodic potential case, namely if we have the periodicity assumption about V, using the technical condition for the nonlinearity, which is much weaker than the Ambrosetti-Rabinowitz technical condition, and using some analytic techniques, it is possible to prove the existence of ground state solution for the non-autonomous problem. In order to find the ground state solution constrained to the Néhari manifold, the functional associated to the Néhari manifold, we give the minimax characterization of the infimum of the energy function with respect to the Néhari manifold, which is defined in this way. Next, I shall consider some perspectives associated to the problem studied in this situation. The first one is to study the Shokart-Pekar equation, which is mentioned in my talk, but in the context of variable exponents, first of all, and then with respect to Stein-Weiss potentials, which appears here with respect to the non-local term, the non-local Shokart term, which appears in the right-hand side. So this is not known. This is extremely important because the presence of the variable exponents creates several difficulties, for instance, according with the regularity of P. And on the second time, this is combined with the Stein-Weiss potentials, which appears in the Shokart term in the right-hand side. I give here some examples. I have discussed problems with Stein-Weiss potential in two papers. One of them published, this is my first paper, published in Compte Rendu in 2021, but in fact it was inspired by some previous contributions of Minbo Yang. I know that Minbo Yang has good connections with Brazil. He studied, spent much time in Brazil, and he was interested in another paper with in Stein-Weiss potentials. So that is why I studied with him and with Joe critical Stein-Weiss elliptic systems, and we were concerned with symmetry, regularity, and asymptotic properties of solutions. That is why I point out that the presence of a Stein-Weiss potential here in the right-hand side would be extremely important, even more if here we have a variable potential. Good. A second direction is to consider double phase equations, or the so-called NQ equations, due to the fact that here we have the NQ Laplace operator, and here we have a contribution, again the same type of contribution, a potential times a power type nonlinearity. So that is why this equation will generate a double phase energy functional, and it is very natural to expect that we obtain different results provided that Q is less than n or Q is strictly bigger than n. And I shall conclude with some of my papers and other papers in this direction. For instance, here I was interested in double phase problems with competitive potentials. Here I was interested in concentrating solutions for several types of problems with non-local reaction. And then I studied also Kirchhoff type equations with critical exponential growth, normalized solutions in another framework, again with problems with critical exponential growth in R2. And recently, last year, I studied normalized solutions for the PQ Laplace equation with mass supercritical growth. Here I give other examples from several points of view. For instance, I would like to point out this paper with Nicolas Papageorgiou and Wen Zhang, where we studied multiple solutions with sign information, this type, for double phase equations with unbalanced growth. And here in this last mentioned paper, concentration properties of solutions for fractional double phase equations. So double phase equations, several types of double phase equations of local type, of non-local type, play a very important role in my research interests. And I would like to thank you very much for your attention.
Thank you, Vicente, for this very nice talk. Please, question? In fact, there are three questions. Two questions from Duichu Luis Iapu in chat of the meeting.
Good afternoon. I would like to make some questions.
Good afternoon.
Sorry?
Good afternoon. I would like to make some questions for the Professor Vicentiu Radulescu. Is possible?
Okay.
Thank you. I would like to know, Dr. Vicente, thank you very much for your exposition, but I would like to know about the consequences this work about the aging state for the stable orbital physical interpretation and numerical construction. Is possible numerical construction?
So this type of solutions were studied by Louis Jean-Jean for the first time, and then by Morose and many other papers. What happens? This is a stationary equation, but the fact that the energy, that the L2 norm, the so-called mass with respect to the Lebesgue space, is fixed, is constrained. It means that if we consider the associated heat equation, then this happens, this is an invariant with respect to the time. So this is important, and this study was inspired, in fact, by phenomena studied, analyzed in physics. So from the physical point of view, from the point of application in the real world, problems of this type are extremely interesting. I was not interested in the study of stability or instability phenomena, because of course they appear in the framework of evolution equations. But I was interested only in the qualitative analysis of solutions of this type, several types of equations. I gave here only some examples, but I was interested in understanding what happens here. From the numerical point of view, I don't know contributions. I don't know contributions in these directions, but I think that it is very natural to try to understand some numerical analysis associated with the normalized solution. But as far as I know, in my research, I didn't find results, meaningful results at least, in the analysis of problems of this type. So this is what I can say to you according to your question.
Thank you, Professor. I would like to add one question. For example, in statistical physics, I get some estimation about the solution using the aging states.
Yes.
For example, I make some estimation in the problem of the vibration with DNA because I have worked Schrödinger equation and estimate the strength, the vibration of the molecule. In that similar, similar, I would like to know if you have some estimation about the solution using the H state.
No. I don't, but I didn't know the applications you have mentioned. I shall try to understand in the near future. I didn't know. I had only some ideas about the fact that we can study some stability properties and so on. But I don't have estimates. Anyway, I keep in mind, and if I find some interesting results, we can keep in touch. We can discuss.
Because one thing, when you normalize the solution, is just the application justamente use the formula for the estimate the solution, using the integral form, like a Rayleigh estimation.
Yes.
Yeah. And for that question, my interest is to apply in this
I understand.
Yeah. Thank you very much, Professor.
Thank you very much to you for your question and for your remarks. I shall consider in the future. Yes.
Thank you, Hernan, for your question. More question? Vicentiu have two questions in the chat of the meeting. The first one is, in the problem 2, the constraint of the norm of the gradient is sharp.
No, it is not sharp. It is not sharp. It is not. This comes from my proof, but maybe it can be improved.
Okay. The second question is, log x minus y is green function of Laplace in R2. Are there analogous results for any greater than 2?
No, I don't know this fact. This is what I know, yes. I told you that there are plenty of open problems in this direction. These are only some directions. I don't know. This is a possibility to continue.
Okay. Thank you, Luis, for your question too. More question? I also have a question, Vicentiu. Is there a normalized solution in the literature for indefinite problems?
Oh, for sure there are. Yes, of course. For sure there, but I don't have in mind at this moment, but I remember that I found. This is another direction. There are plenty of very recent. This is a very modern research. But I remember that I found something like this.
Okay. More question?
In my case, I started from the papers of Morose and Jean at the very beginning, who give the main ideas in the study of explorers. I tried to extend. This is new, for instance, problems with convolution with no-local term of Kirchhoff type, Shokart type, normalized solutions. This is new because they were mainly interested in local equations. Very beginning. The study of local, no-local problems like this type is new. Was studied in the last years.
Okay. More question? So, you are finished, but before you would like